This video will continue our work with 1.6, formally using the limit laws, but really seeing the difficult cases. Thinking about what we learned from 1.5 and the intuitive definition of the limit, we realize that a lot of good things happen, but we have to be prepared for the weird things. And that same thing is now happening with the equations. In the first video, we saw how the nice, simple approach, just plugging in the given x coordinate, and as long as something good happens, we're done. But that doesn't happen. I mean, it does happen a lot, but to really test you on your understanding of limits, you have to handle the tough cases. So we've already seen two. K over 0, we try plugging in our coordinate. If we get k over 0, we know we have an infinite limit, but we have to do work to figure out which infinity. Is it the same infinity? And that's a lot different than 0 over 0, which truly tells us nothing. So now let's keep going. We saw that if we get 0 over 0, we basically have a little process of manipulate, simplify, and then try taking the limit again. So let's continue with that. So I've got one set up here. The limit as x approaches 2 of x cubed minus 5x squared plus 6x all over x cubed minus 2x squared. And if I just try plugging in, 2 cubed is 8, minus 5 times 2 squared minus 5 times 4, which is minus 20, plus 12, all over in the bottom, 2 cubed again is 8, minus 2 times 2 squared minus 2 times 4 is 8 minus 8. And this is another 0 over 0. Now, you're going to see a lot of 0 over 0 when you get to the homework as you go through these videos, but it still is a very important step to make sure you do have 0 over 0. You make a little accidental goof and you should have had 10 over 0, you would be in a completely different situation. Or if you accidentally goof the bottom and you should have had 0 over 1, well, you're done. That answer is 0. There's nothing more to be said. So, again, make sure we don't just jump in, we don't factor unnecessarily, we do what we need to do. And our first step is I try to plug in, but now that I've gotten into some trouble, now I'll go back and I'll manipulate. So in this one, just like I showed in the previous, I'm going to just do a lot of my factoring here. I could see factoring works, the bottom is simple, a GCF of x squared, and then x minus 2 is left behind. In the numerator, well, I've got a common x that comes out, and that's what's left behind. And I could simplify an x here, and that's where part of the reason why I wanted to do this problem. People might think, oh, good, look, I could cross off one x here with this x here, but now when they try and take their limit again, they still get, well, here they get 4 minus 10 plus 6, which is 0. Here, they get 2 minus 2, another 0 over 0. That's just a sign you haven't manipulated or simplified enough. Because yes, while these cancel, that's great, but notice this can still keep factoring. This can factor into x minus 2 times x minus 3. And now I've got x minus 2's that also cancel. Now, there's definitely no more simplification that can be done. There is no more simplifying, and that's what we have left. And now when I plug that in, 2 minus 3 over 2, and I get a final answer of negative 1/2. Again, we had plenty of whole number answers, but fractional, decimal answers, they certainly are going to come up. So this was just another good example. Seeing another fractional answer, getting a negative, seeing factoring is not always just one step. Just because you simplify doesn't mean you're completely set. It's about fully simplifying. Okay, so that was a limit problem. We'll call that one number 1. And now let's keep going and let's see another situation. Let's take a look at the limit of, let's do radical x minus 2 all over x minus 4. And we'll do this one as x approaches 4. Well, first glance, again, we try and plug in, but when we plug in, the square root of 4 is 2, 2 minus 2 is 0, 4 minus 4 is 0. We're in another 0 over 0 situation. Now, most of us look at this and we do not see factoring. There is a very clever way some people see to factor the bottom, but I'm not even going to get into that. I'm going to go into a bigger technique that kind of works all the time here. So factoring, you may see something, but it's a little bit tougher. And for the tougher problems of this nature, that factoring technique is not so super reliable. But watch what we can do. We're in trouble with a radical. And when we have trouble with a radical, there's this concept called the conjugate. The conjugate is very often our algebraic tool to manipulate radicals. The conjugate doesn't matter if the radical is first or second, or if they're both radicals. It's about having the two pieces, and the conjugate has the same two pieces with the opposite sign. So that's what we're going to use. Before I actually show that though, one quick thing. Some people think, well, I need to manipulate. Oh, I don't like square roots. I'll square. But if you square this, you're changing the function. So when we change the function, when we factor, we did that little previous exercise to show the graphs are essentially the same if you simplify after factoring and compare the functions from before and after. But if you start squaring, you're getting a completely new function. There's no reason at all to think that limit would connect to your original limit. So I'm going to use the conjugate. The conjugate here would come from the top, would be radical x plus 2. But I can't just multiply the top. Again, I need to manipulate, not change. So to manipulate this, whatever I do to the top, I'll also do to the bottom. So I'm multiplying this times my original function. So in essence, I'm multiplying by 1, and by multiplying by 1, you don't change anything. So again, it's a manipulation, not an actual change to the function. But now, actually multiplying, I'm only going to multiply out the conjugate pair. The bottom, in this case it's the bottom. We'll do a follow-up in a second. I'm just going to leave those. They're still attached by multiplication, but I don't want to actually multiply. Remember, we're ultimately looking to simplify, and if you start multiplying this out, you lose the ability to cancel like terms. Now, look what happens when I multiply the top. Radical x times radical x gives me radical x squared. I'll simplify this in a moment. I'm just being very literal here. This times this gives me plus 2 radical x. This times this gives me minus 2 radical x. And then this times this gives me a minus 4. What we just did, if we look at this little cleanup part, should happen every time if we use the correct conjugate and multiplied it correctly. Sorry, here we are. This is what I got when I multiplied it out. And this first simplification, squaring a square, that just cancels and I just get a plain x. Plus 2 radical x minus 2 radical x. These two are like terms, and they not only combine, they cancel, and the minus 4 is still hanging out. So the conjugate is just meant to clean this part up so that this piece no longer has a radical. But now looking at this problem, do you notice something else nice that happened? Now that I've cleaned up the top, now I've got a matching factor that cancels top and bottom. And that's why I was saying you don't want to actually FOIL these out. You don't want to actually distribute. You'd lose that ability to cancel. You'd lose that, you'd even see that there is a chance to cancel. So I had to technically multiply top and bottom to just manipulate and not change the function, but I really only multiplied the conjugate pair, and that allows me to cancel this. This leaves me with 1 over radical x plus 2 as x approaches 4. Still have my limit notation, and now I've simplified a lot. I'll try and retake my limit. 1 over radical 4 plus 2 will give me a final answer of 1 over 4. That's a tough one, everybody. Going back to the beginning, some people are really clever and can force this to be the difference of squares, factor this as radical x minus 2, radical x plus 2. But like I said, not easy to see, and it's not always just quite so perfect. So let's do a follow-up. Let's take a look at number 3. Now let's take a look at the limit of 18 minus 2x all over, let's do 3 minus radical x. And we'll do this as x approaches 9. So I look at this one, I plug in, 18 minus 2 times 9, 18 minus 18 is 0, 3 minus square root of 9, 3 minus 3, another 0 over 0. So another 0 over 0, but not similar to this first one where I had the ability to factor. There's no good factoring here. Again, a 2 can come out of this, but that doesn't get you very far. Ultimately, I've got to realize the radical is where I'm getting in some trouble. So again, I need the conjugate. This time the radical is in the denominator and the radical came second, but the conjugate, I look to the radical to find its conjugate pair. Same two pieces, doesn't matter if the radical is first or second, the middle sign just changes. And now I can't just do that to the bottom, I'd also have to do it to the top. But now this time I'm gonna leave the top alone. And this time I'm going to multiply out the bottom because that's where the conjugate pair is. When I factor this out, I mean, some people get very quick and they start to realize that these situations, that if you use the conjugate pair, the middle terms will always cancel, so they could just do first times first and last times last. But especially if you're just learning this, a lot of people like to do it out entirely. So I'll say it, but I won't write everything. 3 times 3 gives me 9. Then I get a positive 3 radical x and a negative 3 radical x, which would cancel. It's kind of a confirmation I'm on track. But now at the end, I get a minus radical x squared, so it becomes a minus x. And now, not quite as perfect as the first one, because now when I did this first one, as soon as I cleaned up using the conjugate, I saw a common factor that canceled. Here, I'm not quite there, but I'm just about there. Now I can go back, and now that's why it wouldn't have hurt if you took the 2 out of here, but ultimately you needed the conjugate. You take a 2 out, even little things. This, I take the 2 out, I get a perfect 9 minus x, these cancel. So I have 2 times 3 plus rad x. You could put over 1. When you have something left in the denominator, keeping a numerator and a 1 in the numerator is essential. But here, over 1 or not writing that, that's all the same. That's just your choice. And now I can actually take that limit. 2 times 3 plus radical 9, so 3 plus 3 is 6 times 2. And our final answer here is 12. But just go back here for one quick second. If this was a 9 minus x and this was an x minus 9, just a quick reminder, when you have the exact same terms with the exact opposite signs, you could just factor out a negative and then those will match. So that's our second big 0 over 0 situation. 0 over 0 when we have some issue with a radical, and then we can use the conjugate. Okay, so let's keep this going. Number 4. We're still evaluating. I'm not going to recopy the directions from the page, but we're still evaluating the limits. And now in number 4, let's take a look at the limit as x approaches 3, 1 over x plus 2 minus 1 over 5 over 3 minus x. This is a big, ugly, fractional type of problem, but we'll see how to handle it. But first things first, I'm going to plug in. And when I plug in here, 1 over 3 plus 2, I get 1/5 minus 1/5, so that's 0 over 3 minus 3. And we're getting 0 over 0 one more time. But a third case of 0 over 0. We saw the situation where we can factor, so we did. We saw the situation where we had a radical, so we used the conjugate. And now this third situation, this is a compound fraction. I'm going to simplify the fraction. Now, there's 2 little techniques that people do in this situation when it comes to simplifying their fractions. Number 1 is, how do I want to phrase this? They kind of get rid of this in one big step. but with a little work with common denominator. I prefer, especially for some people who are a little rusty, I prefer to show it in 2. So algebraically, we may be slightly different in our approach, but we'll still get to the same place at the end here. Okay? So in this next one, let's take a look and let's think about first just looking at the top. Common denominator, well, this has an x plus 2, this has a 5. The common denominator is 5 times x plus 2. So to get that common denominator, well, it needs a 5, but whatever I do to the bottom, I also have to do to the top. And over here, it needs an x plus 2 on the bottom, but whatever I do to the bottom, I have to do to the top. So I still have my limit. My denominator, I'm doing this so I get a common denominator, so I could write that as one fraction, 5 times the quantity x plus 2. But now my numerator, well, from here I got 5 times 1, 5. Over here, careful everybody, this is minus 1 times x plus 2. So I'll be literal here. I'll write minus the quantity x plus 2. And not to forget, this is still all over 3 minus x. But over here, distributing that negative, realizing a lot of people are tempted to just cancel. Hey, the 5's cancel, the x plus 2's cancel. That's garbage, everybody. This subtraction blocks you from canceling that. You need stuff only attached by multiplication to then do canceling from the top and bottom. So this subtraction tosses that out the window. I need to actually distribute that. And now when I clean that up, 5 minus x minus 2, that becomes 3 minus x over 5, quantity x plus 2, all over 3 minus x. And now, you know what, actually, I'm sorry, everybody. Let's make that x minus 3. Doesn't change anything here. That's still 3 minus 3 in the beginning. But this will give me a chance to show you something I mentioned on the previous page. So now this is an x minus 3. And now this is good. You can distribute this as if you want, but ultimately we're looking to cancel, to simplify. This is our manipulation. By getting this to be one fraction, but now by having this whole top as one fraction, and this is divided by x minus 3, which I could treat as divided by x minus 3 over 1, the point of making this one fraction here was so now I have a fraction divided by a fraction, so I can multiply by the reciprocal. And now I've cleaned up my fraction. But now it's not just that I made it a clean fraction instead of a complex fraction. I'm still looking to simplify. And that's where, this is why I made this little swap here, why I wanted this to be an x minus 3. We're not always going to be so lucky, whether it's the conjugate or the fraction, that doesn't matter. We're not always going to be so lucky that everything just cancels perfectly. We saw in the previous one, well, I had to factor out a 2, and then things factored perfectly. Here, these are too similar. They don't cancel because they're not exactly the same, but factor a negative out of either one. And it doesn't matter if you factor it out of the top or the bottom. In a fraction, a negative in the numerator or a negative in the denominator, kick that out and treat it as a negative out in front. It's all the same thing. So I'm going to kick a negative out of this, so I get a negative 1, and then it becomes x minus 3. It literally becomes minus 3 plus x. I just changed the order, so now these cancel. And now I'm finishing up this problem. I've got the limit, x approaches 3. All I have is a minus 1 left on top, minus 1 times 1. The bottom, I have the 5 times x plus 2. And now we could finally finish. Minus 1 over 5 times 3 plus 2, minus 1 over 5 times 5, minus 1 over 25 for our final answer. Okay. Very good so far, everybody. These are tough problems. Everything we've been doing, you're seeing the algebraic way to manipulate. This gives us a lot of good reminders for different techniques and tools that we'll continue to use through calculus. Now, you could still use your calculator. You could still make XY charts for every one of these. But do you notice how the functions are getting more complicated? Even with a graphing calculator, just trying to plug something like this in, keeping track of all your fractions, there's so many ways to goof that up. So, as we said at the beginning, the calculator is an option, but for most people at this point, it kind of becomes a backup option. If you're not seeing a good way to proceed, you feel like you're getting stuck, well, that's a backup. Or you just want to do something to check your work that you did algebraically, that's certainly a good option as well. Okay, one more big case with 0 over 0, and we still have the piecewise functions that we need to discuss. So, number 5, this is the one that completely tosses the calculator out the window. Let's take a look at the limit as h approaches 0. And let's take a look at that limit, and we'll have x plus h quantity squared minus 5 times the quantity x plus h plus 1 minus the quantity x squared minus 5x plus 1, all divided by h. Now, this should be a spot where you say, what the heck is h doing here? Sure, x is a common variable, x's and y's, that's how functions work. We've looked at limits by thinking about graphs where we only have x's and y's. Where did h get in here? This is setting us up for the derivative. We're not there yet. Again, this is another one of those building places. Right now, we just have to get used to dealing with h, and then we'll start to see what the purpose of h is. So this is what we kept saying. The 1.4 video, we started talking about tangent lines and some idea of rates of change using the idea of velocity to get that idea started. All that is going to come back with the idea of the derivative. But the limits are the tools that are going to get us there. So again, what is h doing here? Well, right now it's just a variable. And to notice that even though this looks messy, you only would plug this in for h. So if you still, our first step, plug in the variable, h is 0, I get x squared minus 5x plus 1 minus that exact same thing. So algebraically, everything would cancel. You get 0 on top, and then h in the bottom, which goes to 0. So this still gives me a 0 over 0. This is still one of our tells me nothing forms, and a form that I still need to manipulate. But even though this one is ugly, and even though this one combines x and h, this one is actually a tiny bit friendlier because that this one, what can we do? Well, this is the one where we can actually just do the algebra. We're not looking to factor. We don't have any radical or fractions here. We're just going to deal with this. We're going to deal with this, and we'll deal with this by literally squaring. X plus h squared. Make sure you don't just distribute the square here. You have to FOIL this out. You get x squared plus xh plus xh, which will combine to 2xh. Then you'll get an h squared at the end. Distribute the minus 5. The plus 1 is hanging out. Distribute the negative. Good habits. Still keep your limit notation. And now, as soon as we get rid of all those parentheses, by just literally multiplying, distributing, doing what we can, now we'll notice some simplifying starts to present itself. Look at the top. You've got like terms, but not only are they like terms, several of them cancel. Positive x squared and minus x squared, cancel. Minus 5x, positive 5x, cancel. Positive 1, negative 1, cancel. So that feels like we've done some nice simplifying. But if we think we're done and we just try and plug in h is 0, well, 2x times 0 plus 0 squared minus 5 times 0, you just got a big 0 on top, still over 0 in the bottom. So we're not all the way done, but now that we've done so much cleanup, can you see the way to finish this one? The big thing in these h problems is that you will notice, this is not a coincidence, you will notice that plain h in the bottom, and that's always going to have to cancel if we're going to get rid of the divide by 0. So in this case, do we notice that now that we've cleaned up the numerator, everything in the numerator has an h? So either I literally divide each term by h, and that allows me to simplify, or you can factor out a common h, and that allows you to cancel. But now, that is our last step of simplifying. So that is the tiny little advantage with the h problems. You know you're going to have to cancel that bottom h. And now to finish, we still plug in h is 0. That's our end game. We can't plug in anything for x, so our final answer, 2x plus 0 minus 5, is 2x minus 5. That's the last little difference here. And again, when we get to the derivatives, we'll understand why we can have an x left. But go back in the previous ones. When your limit is over variable x, and that's the only variable, when you're done, you're only going to get a numerical answer. That as you approach this x, this is the y you approach. We don't have that same relationship here because we're not approaching an x value here. We're approaching an h. But when we're done, here, if you're approaching an x, there are no more x's in your answer. Here, if you're approaching an h, there are no more h's in your answer. So let's do two more. And now let's finish these h problems, and let's take advantage and combine a few ideas. So number 6, for number 6, let's take a look as h approaches 0, radical x plus h minus radical x all over h. In a good situation here, still an h, let h go to 0, you get radical x minus radical x, 0, all over h, which goes to 0, so it's still a 0 over 0. But now, see this previous one, it's not so much that it was an h value that led us to the cleanup that we did, the manipulation we did. It's the nature of what was here. What can we do with this? Well, we had parentheses, we had exponents, and we had things that we could manipulate by literally multiplying. So that's what we did. We don't have that situation in number 6. What we do have is another radical situation. So we're going to use the conjugate again. This time the conjugate will have radical x plus h plus radical x. Both of them have the radicals. That doesn't matter. I still just change the sign, keep the same order. And whatever I do to one piece, I have to do to the other. My denominator, I'm just going to set that up that they're attached, but I'm not going to distribute. I'm only going to actually multiply out the conjugate pair. Rad x plus h times rad x plus h is x plus h. Middle terms cancel. Plus rad x plus h minus rad x plus h. Like terms with opposite signs that cancel. And then at the end, minus rad x times positive rad x is minus x. This one actually, again, worked out pretty nicely. X minus x cancels. Now all you have left in the numerator is h, so that cancels with that h down here. So we're left with 1 over radical x plus h plus radical x. And now when I let h be 0, 1, you could literally leave rad x plus rad x, but you can add those together to get 2 radical x. So a tough conjugate problem, and one that combined an h, but it really was the radical that led us to the conjugate. And you'll notice the same thing in number 7. Let's take a look at h approaches 0. Let's look at minus 10 over x plus h plus 10 over x all over h. As h goes to 0, minus 10 over x plus 10 over x, cancel, 0, all over 0. Another 0 over 0. And now we're back in the compound fraction problem. So, common denominator here first, x times x plus h. Remember, you still need 2 separate pieces. This is combined by addition, so you can't say this piece is already copied here. They need to be connected as multipliers. So this needs an x over x, This one needs an x plus h over x plus h. My denominator just for the top will be x quantity x plus h. My numerator, I get a minus 10x here. Over here, I'm already going to distribute. I get plus 10x plus 10h. And not to forget, we're still all over h. Back up here, the minus 10x and positive 10x cancel. 10h over this. This is h over 1. I multiply by 1 over h, multiply by the reciprocal. All this addition subtraction is gone, and that's important. That's what allows me to cancel the h off here. I have 10 over x, x plus h, as h approaches 0. And I'm finally ready to take the limit again. As h goes to 0, that's 0. So I get 10 over x times x, 10 over x squared. Okay, our last tough one. We have to talk about piecewise functions. If you go back and look at the graphs, and again, everything we're saying, you truly understand limits when you show you could handle all the tough cases. And when you look at the graphs, most of the tough cases were random open holes, asymptotes. Well, those are things we've covered with 0 over 0 and k over 0. But the other tough aspect were all those weird breaks and jumps. Those breaks and jumps entirely originate with what we call piecewise functions. So let's take a moment to talk about piecewise functions in general, remind you how they work, how they're set up, and then we'll lead into limits, and that'll finish this video and wrap up all of our techniques for all the different situations. Again, the trig functions, we're still kind of leaving them a little separate. We'll come back to them in chapter 2 and do some similar work, but there's still plenty of little situations and techniques to get familiar with here. So for this one, I'm going to look at a piecewise function, and I'm going to have this have 3 pieces. I'm going to keep them fairly simple. We're going to let the first piece be x plus 2 for x values when x is less than or equal to -1. Our second piece will be x squared. We'll keep that one when -1 is less than x is less than or equal to 2. And then last, we'll have the square root of x, and that'll be for when x is greater than 2. So what does the graph of a piecewise function look like? Basically what it looks like is take all these 3 graphs, but then cross off the pieces that don't match up with these given x's. Okay? So how do we go about doing that? Well, for this one, x plus 2, that's just a nice straight line. That would be this straight line. Y-intercept of 2, my slope is 1, so up 1 over 1. But that would not be the graph everywhere. It would only be the graph when x is less than or equal to -1. So there's -1. It has the equality, so this will become a filled in point, and I will get rid of all of the rest of it. All that is gone. My second piece, y equal x squared, that's the parabola at the origin, but my parabola is not going to go everywhere. It's only going to go back to here, and on this side, I'm going to stop it when x is 2, because that's where it stops here. And then my last piece would be the square root of x. I kind of call that one the hook. It's a hook that comes out of the origin, but I don't want the whole hook. I only want the hook past x is 2. So I'd actually have an open circle right there, and that would be the continuation of my hook. So again, getting rid of this, that's my graph. I've got a straight line, then all of a sudden I jump into a U piece, and then I've got a big jump over here. So it's got a lot of action because it's got these separate pieces. So for the most part, when it comes to taking limits, remembering the idea of approaching the x value, as long as we check left and right and our close x values all fall into the same piece, Well, that's not complicated. So if I asked you what is the limit of f of x as x approaches -3, well, every value that approaches -3, from the left, -3.5, -3.2, -3.1, from the right, -2.8, -2.9, -2.99, every single x I said is an x value less than or equal to -1. So I don't care about the other pieces. For this first one, for these particular x's, I only need to be concerned with the x plus 2 piece. And now that I've got the equation, and there's only one equation in there, now I can take it using my limit laws. I plug in the -3, nothing fancy happens here, and I get an answer of -1. And similar things, everybody. If I took the limit as x approaches 0, everything that approaches 0 would be here, so I'd only need the x squared function. If I took the limit as x approaches 4, well, every value that approaches 4 would be greater than 2, so I'd only need this function. So why are piecewise functions tricky? They're tricky at these spots. I informally call these the turning spots. The spots where my different pieces might change, where the piece I have to focus on might change. That's where they get difficult. And from my graph, you can see -1 will actually be okay. Even though these were two random pieces of graph, they're coming together at -1. We'll get an answer. But come over here and look at x's approaching 2. From the left, we're up here. From the right, we're down here. We're not approaching the same point. So the graph, we already know how to handle it that way, but if you're not going to draw the graph, these are not always so easy, by the way, as well. So it's not just, you don't feel like drawing the graph. It's not easy to draw these graphs. So we want to be able to handle it using the equation. So let's take a look at both of those. If I take a look at x approaches -1, and then separately as x approaches 2. Well, again, experience, we'll realize that through experience, these will be tougher because we're dealing with the turning points. And it's not that easy, everybody, to just say, hey, that's where the equality is. Use this first one. Hey, that's where the equality is. Use the second one. This is not saying what is f of -1 or f of 2. If that was the question, that is what we would do, but it's about the limit. So as your x's approach -1, and as you approach -1, you're going to get values that fall in here. -0.8, -0.9 are in between these two values, not less than -1. Same thing with 2, 2.3, 2.2, 2.1. All those x's are legitimate x's that approach 2, and they're here, not here. So what we're going to do when we have one of these turning points, we're going to have to break it down. Break it into the two sections. If you approach -1 from the left, -1.2, -1.1, all of those x's are in this category, so you can use the x plus 2 function. And if you approach -1 from the right, -0.8, -0.9, -0.99, now all those do fall into one category, and that's where I can use the x squared. But now the left and the right are done. For me to finish both of these, I'm still just going to go back to plain old -1. -1 plus 2 is 1. -1 squared is 1. My limit from my left equal my limit from my right. This answer is 1. Now let's try that with 2. 2 from the left, 1.7, 1.8, 1.9. My x's fall into this category, so I will use x squared. And some people just keep going. Now I could just plug in 2, and as x approaches 2, my y would approach 4. And now, thinking about approaching 2 from the right, so 2.3, 2.2, 2.1, well, all those x's would fall in here, so I'll use the square root of x, and when I plug in that, I'll get the square root of 2. My y from the left does not equal my y from my right. This limit does not exist. So that's, again, trying to do a nice introduction, a reminder of piecewise functions, a common way that they might look, how their graph might go with them, but starting to establish how we'll handle the limits. And now let's finish this video with 2 piecewise functions and a few limit questions. So let's look at, we'll have the function g of x, and we'll do g of x in a similar way, a little more complicated, but we'll still do 3 pieces. Let's look at, let's do 3x plus 4 when x is less than -2. We'll have x squared plus 1, -2 less than or equal to x less than 3. And we will have, let's do 4x minus 2 when x is bigger than or equal to 3. So you are given this piecewise function. Let's evaluate, number 1, the limit of g of x as x approaches 1. Number 2, the limit of g of x as x approaches -2. And number 3, the limit of g of x as x approaches 3. If you want to take a moment to pause, take a shot at these yourself based off what we just did, and then watch, that's certainly fine. But now I'm going to jump in. This first one, every time we deal with the piecewise function, not just this x, but the x's around it, which category do we fall into? And when we do that here, x approaches 1, everything from the left, 0.7, 0.8, 0.9, from the right, 1.2, 1.1, 1.01, any x value that approaches 1 is between -2 and 3. So nothing fancy here. 1 is not one of my turning values, so I get to just use one piece. I'll just use the x squared plus 1 piece, and now when I plug that in, I get 2, and I'm done. But now number 2, now I am dealing with a turning piece, and some people just get used to it. I'm going to be dealing with these 2 pieces. This is where the definition splits at -2, so these are the 2 pieces that'll be in play. But you could still take that nice long approach. As I let x approach -2 from the left, talking about -2.3, -2.2, -2.1, we're here. So I'll use the 3x plus 4. And when I let x approach -2 from the right, -1.7, -1.8, -1.9, we're here, so I'll use the x squared plus 1 function. And I could rewrite more. I'm being a little quick with my notation here, but it's enough. Being clear how you're breaking it down and which piece you're using. But now I use -2. -6 plus 4 is -2. In this one, -2 squared is 4 plus 1 is 5. And it doesn't matter how close or far away these are. If these 2 values are not the same, that gives me a limit that does not exist. And now let's wrap this one up. Number 3 here, the limit of g of x as x approaches 3. Well, now again, 3 is one of those turning points, but still the long way. And again, I'll write this one out even more. I have no problem with you writing this. This is enough for me. But if you want to be completely thorough, I did the same thing with the k over zeros as well. Instead of rewriting the whole limit and the function, just get what we need. There we just needed the left or right, and then we needed the signs. Here we just need the left or right and the appropriate piece. But you could write it all out as x approaches 3 from the left of g of x, 3 from the left, 2.7, 2.8, 2.9. We're thinking about, well, not thinking, we are here, so I'll use the x squared plus 1 function. And if I take the limit as x approaches 3 from the right, 3.3, 3.2, 3.1, those x's fall in here, so we'll use the 4x minus 2 piece. Now I have them both set up. The left and the right have served their purpose. I don't need to plug in 2.7, 2.8, 2.9. I can, but I'd be going back into one of these setups. I wouldn't have to do the left and the right, but I could make this whole exact chart. That's essentially what we're doing here, but we're getting to the easier part, just plug in. Nothing bad is gonna happen here. I plug in 3, I get 9 plus 1 is 10, and here I plug in 3, I get 12 minus 2 is 10. They're 10 from the left and the right. This limit equals 10. One more, everybody. One last piecewise function. This is a very common way. We'll see we don't get piecewise functions throughout this class. We see a bunch of them in chapter 1, a tiny bit in chapter 2, and then we kind of focus on more normal functions. But in the early going, a lot of our piecewise functions look like this, but then we also get some that look like this. One more piecewise function. Let's look at h of x is x squared minus 25 over 2x minus 10 when x does not equal 5, and it equals 4 when x equals 5. So this function, we'll use this function to finish the last two. Realize, everybody, I have to give you a piecewise function. I'm not asking you to make up a piecewise function here. I'm giving you a piecewise function and then asking you limits. So we'll do number 4. We'll take a look at the limit as x approaches 0. And then number 5, the limit as x approaches 5. This one is nicer. 0, anything that approaches 0 is not 5. So even though this doesn't have the inequalities, it's all about what x is. When x is 5, we get this y. If x is anything else, we use this to get the y. Well, 0 and anything that approaches 0 from the left or the right is not 5. So some people, they see a piecewise function, and now from what we did up here, they think these turning points, they have to set up the left and the right. If you did x approaches 0 from the left, you'd use this. And then set up x approaches 0 from the right, you'd still use this. So it's not always just about setting up the left and the right. It's always just considering both sides. And that one is very similar to this first one up here. 1, every value that surrounded 1 fell neatly into one category, so I only needed one piece of the definition. That's it. But when my approaching values fell into 2 categories, well, then I needed to set both up. Here, everything that approaches 0 is not 5, so I'm only going to need this definition. And even if you're thinking about factoring, don't. First plug in. You plug in 0, 0 minus 25 over 0 minus 10. You get negative 25 over negative 10. That's an okay answer. We could make that a little bit better, right? We could simplify that. That is plus 5 over 2. 2.5, never have any problem with with decimals if you prefer, but there's also nothing wrong with leaving it as a fraction, even an improper one. So 5 over 2. So one more time, you're not dealing with a turning value. Things are not that bad. Just because it's a piecewise function, you just got to make sure you're using the right piece. But now even this one, now I am dealing with the turning value, but even this one isn't that bad. Because as this nature, if I let x approach 5 from the left, 4.7, 4.8, 4.9 are all not 5. And same thing if I approach 5 from the right, 5.3, 5.2, 5.1 still are not 5. So this one still seems friendly. Because we only need one definition, but now we realize that just because it's a piecewise function doesn't mean the plug-in part is easy. You plug this in, you get 25 minus 25 over 10 minus 10. We're still back in a 0 over 0. So this is just trying to point out, just because it's a piecewise function, k over 0 can come up. 0 over 0 can come up. You could break things down. The left-right approach is more necessary more commonly in this type of a piecewise function, and this one It's more common you might get a 0 over 0, but you really should be able to take each one individually, think about the left and the right, think about the appropriate pieces, and then solve the limit as necessary. So this one, we're back to a factoring situation. Take out a 2 in the bottom, x plus 5, x minus 5. I see the matching x minus 5s. And just because I'm running out of room, I normally would recopy this, but now I'm just going to jump to the answer. As x approaches 5, 5 plus 5, 10 over 2, we get an answer of 5.